In this video, I'll be teaching you about triangle inequalities. So the big idea that we need to cover before we start this is understanding that the largest side of a triangle is always opposite the largest angle, and the smallest side is always opposite the smallest angle. So for example, in our triangle over here, the smallest angle that we have is 24 degrees. When we look across the triangle at the side that is opposite of that angle, we see the side length of 6. Compared to the other sides, that is the shortest side, and compared to the other angles, that is the smallest angle. That's also the case when you look at the largest angle, so in this case angle B at 97 degrees. Across the way from that triangle on the other side is the side that is 15 centimeters, which is the longest side of the three. So this will always be true in a triangle, that the smallest angle is across from the smallest side and the largest angle is across from the largest side. So now that we've kind of talked about that common rule, you can go ahead and pause the video and try to apply that to these two triangles here. When you're ready, you can press play. The shortest side here is side KL. After that, we have side JL. And after that, we have side JK. So I'm just listing them in order from smallest to largest. So this means that the smallest angle would be across from the shortest side. That means that angle J would be the smallest. Our next side in order from least to greatest was the side of 25, or side JL. So opposite of that would be angle K. And then our longest side is 28, so we look across it at the largest angle, which would be angle L. And that's how we can put them in order from smallest to largest. We can repeat the process over here, but kind of go in an opposite way. So in this one, we can see that we are given a right angle, which is 90 degrees. This one is 33, so that must mean that this last angle that's missing is 57, because we know that all of the interior angles of a triangle add up to 180, and if we have a right angle or right triangle, we know that the other two smaller angles must be complementary, so they need to add up to 90. So 33 plus 57 there gets us 90. So now that we have the angles marked, we can put them in order from least to greatest. So the smallest one there is angle G at 33 degrees. Then we have angle D and angle F. From there, we can decide on the sides. So the smallest angle is across from the smallest side. So I look across from the angle, and I see that the side DF is across from the smallest angle. So that must be the smallest side. Then I look at my next largest angle, which is 57. That is across from side FG. And then our largest angle was 90, so the side across from that is DG, and that will be the longest side in our triangle. So just looking for the smallest angle or smallest side, and then across the way to find the largest side, shortest side, whatever it might be. So kind of going along with that now, we're learning the triangle inequality theorem. And the triangle inequality theorem tells us that the sum of the lengths of any two sides of a triangle must be greater than the length of the third side. So for example, in this triangle, if I take AB, which is the red side, and I add it to BC, that length must be greater than AC for this to be a triangle. If that inequality wasn't true, then this set of three sides would not make a triangle. They wouldn't be long enough or too long to, or they wouldn't be long enough to form a triangle. So their lengths might be too short and make something more like this, where those two other sides up top don't attach because they're too small. So we have to check it on all three sets of sides, so you add up each pair and make sure that it's longer than the third side that you haven't touched. All three inequalities must be true for this to work. So if it's asking you, is it possible to construct a triangle with these given side lengths, we need to set up each of these inequalities and check them all. So in this first one, 6, 7, and 11, I'm adding 6 plus 7. Well, that's 13, and that is greater than 11, so that first one works. Then I need to take 6 plus 11, say that should be greater than 7. Well, that's 17, and that is greater than 7, so that works. And then I'm going to take 11 plus 7, which should be greater than 6, and that is because 18 is greater than 6. So since all three of these inequalities were true, we can say, yes, these three sides would create a triangle because the triangle inequality theorem held up here. We're going to repeat this process for the other examples. You can pause the video and try them on your own if you'd like. We have 3 plus 6 should be greater than 9, 3 plus 9 should be greater than 6, and 6 plus 9 should be greater than 3. When we go through and simplify all these, we get 9 is greater than 9, 12 is greater than 6, and 15 is greater than 3. Well, these bottom two inequalities are true. This top one says that 9 should be greater than 9. 9 is greater than or equal to 9, but since we don't have that or equal to part of this inequality, this does not work, which means these side lengths would not form a triangle. Then we have our last example here, so we're going to take 18 plus 34 and say that that needs to be greater than 39. We can take 18 plus 39 and say that that needs to be greater than 34. And 34 plus 39 needs to be greater than 18. So when we go ahead and double, we can check these and we can see that 18 plus 34 is definitely going to be greater than 39. When I add them together there, I get 52 is greater than 39. Then I have 18 plus 39, which gets us 57, greater than 34. And our last one here of 73 is greater than 18. So all three of those inequalities were true, and we can say, yes, this set of sides would make a triangle. So next up we have this rule that basically uses the triangle inequalities theorem but helps us kind of write it in a compound inequality rather than in separate ones. So the length of each side must be greater than the difference of the other two sides but less than the sum of the other two sides. So that's telling us that if I take two sides and subtract them, it must be less than that third side, but that third side must also be less than those other two sides added up. So this is helpful when you're given two sides and you're asked to figure out what the range of the third side could be. So if I already know that two of the sides are 12 and 8, so say I have this triangle starting to be formed, 12, 8, and now we don't know how much this is, but we're going to call it x. And we're going to see how big is x allowed to be so that this fits in the triangle inequality theorem. Well, we could do it two ways. You can either stick with what you know and solve each of these inequalities on your own. You could say 12 plus 8 needs to be greater than x. You could know that 12 plus x would need to be greater than 8, and 8 plus x needs to be greater than 12. If you solve each of these, we see that 20 needs to be greater than x. This one tells us that x would need to be greater than negative 4, and this one tells us that x just needs to be greater than 4. So this negative 4 one doesn't really help us because if we go ahead and put all of these on a number line, negative 4 is down here, 4 is here, and 20 is back here. So if we know that x needs to be less than 20, that's going to go somewhere to the left of 20. X also needs to be greater than negative 4, or just greater than 4. I'm ignoring this one because I'm talking about distance. The distance of our side of our triangle could never be negative. So that inequality, although it is in our list of triangle inequalities, the one where you end up with a negative number, we're going to ignore because it cannot be a negative distance in our triangle, otherwise it wouldn't exist. So we can see now that the two that were valid were the ones that were x is greater than 4, but x is less than 20. So we can write that as a compound inequality as 4 is less than x, which is less than 20. We could have also gotten there using the rule. So if x is the side that we're looking for, we're going to put that in the middle, and we're going to say that the difference, so 12 minus 8, needs to be less than x, but the sum needs to be greater than x. So 12 minus 8 is 4, and 12 plus 8 is 20, and either way we end up with this compound inequality that 4 is less than x, which is less than 20. So x must be somewhere in that range for it to make the inequalities true. So I'm going to use the rule to do this one here, and I'm going to say that the difference, 9 minus 5, must be less than x, our third side that we don't know, which must be less than the sum of the two sides. So we have 9 minus 5, which is 4, should be less than x, which is less than 14. That means that x must be somewhere between 4 and 14 for this triangle inequality to work. So next we're going to look at the Hinge theorem, and this kind of goes along with our triangle inequalities because we're able to come up with some statements of which sides will be greater than others. So the beginning of the Hinge theorem states that if the two sides of one triangle are congruent to two sides of another triangle, and the included angle of the first is greater than the included angle of the second, then the third side of the first triangle is greater than the third side of the second triangle. So there's a lot going on there. All we know right now is that these sides are congruent, We have this set of sides that are congruent, and we're given the angles that are formed by those sides meeting. So I've got these two sides, and we're told that this angle is 88 degrees. This one is 35. So because these two sides are congruent, then there's only so much or so little that we can make these other third sides based on the triangle inequality theorem that we were just looking at. We obviously don't know the numbers. All we know is that they're the same. So since we can't really give a specific amount, all we can really say is which one's bigger, which one's smaller. And you can just kind of look at it based on the picture. A wider angle or a larger angle is going to create a longer side across from it, versus a smaller angle is going to create a smaller side. And we know that we can then say that ST will be less than XW, and that is because of the Hinge theorem, which stated that since that angle R was less than angle V, and those other two sides that were creating those angles were congruent, that means that that side ST must be less than side XW. So that's what our Hinge theorem states. You must have two sides that are congruent, and then you need to know those angle measures, and that's how we can make that decision about the sides. We don't know the exact length, but we are able to say which one is larger or smaller. So next up we have the converse to that. Remember, the converse is just reversing the statement. So this time we're told that we've got congruent sides, so CB is congruent to FE, and then we have this other set of congruent sides of AC and DF. Well, we don't know the angles in between. However, we can see that those sides across from them are given. So the side across from angle F is 9, and the side across from angle C is 12. So since the side DE is less than the side AB, the converse to the Hinge theorem tells us that angle F, the one that was across from DE, will be smaller than the angle C that was across from the side that was 12. Since those included sides were congruent and those sides across from them had those different sides, we automatically know which angle will be smaller. Again, we don't have enough information here to say how much did these angles measure, how much are those other sides worth. We don't know that. All we can say is that those two angles, how they will compare in terms of which one's greater and which one's smaller. So we're going to do a little practice with the Hinge theorem and the converse on these 4 examples. So if you'd like to pause the video and try it yourself, you can. We're going to first look and make sure that we have congruent sides marked on both of these. So this side is congruent to that one, and these two sides are congruent. So we're using the angles that are given to us here to make the decisions on which ones will be smaller. So angle C is 105 degrees. That is less than angle F, which was 110. So that tells us that the side across from angle C, which is AB, will be less than the side that was across from angle F, which is DE. And that is what our Hinge theorem allows us to say. In the next one, we have 2 triangles sitting next to each other. We can see that we have sides that are marked as congruent, but we aren't given a second side that is congruent. However, these 2 triangles are sharing a side, which automatically means that those sides must be congruent to each other because they are the same side. So they're the same piece of triangle side. They're just forming the side of 2 different triangles. So they must be congruent because they are the same line. So that means that we have 2 sets of congruent sides, and we're given the length of the sides across from the angles. So we can say that this side 7 that is across from angle 2, 7 is less than 8, and 8 is the side that is across from angle 1. So that means that just by a little bit, angle 2 must be less than angle 1. This was from the converse of the Hinge theorem, because we're talking about sides and then letting it determine the angles. Here we have, we don't have any congruent marks, but we can look at the measures. These were both given to us as 6, and again we have the shared side. So those sides must be congruent. So 65 is across from 7 and 70 is across from x. Well, 65 degrees is less than 70 degrees, which means that that side 7 must be less than the side worth x. So x must be greater than 7 is the conclusion we can come to from here. This is our Hinge theorem because we knew the angles this time and we're making a statement about the sides. Finally, we have this last example where we're given that 12, this is worth 12 and this is worth 12. And again, they're sharing a side. So the side in the middle must be congruent. So then we look across at the angles and the sides. We can see that 11, which is across from this angle, is smaller than 14, which is across from this angle. So since 11 is less than 14, we can say that the angle across from 11, which is 2x plus 1, must be less than the angle that's across from 14, which is 74. Now we need to solve this. So 2x is less than 73. We divide and we get x is less than 36.5. And that would be our inequality about the angle measure there. And we would know that that angle would actually need to be, as a whole angle, that would need to be less than 74 degrees. But specifically x, we've solved for now to know what x must be less to make that angle worth less than 74 degrees.